Okay, getting into the last objective of this module, or official objective, we're looking at texture analyses of our images, and really that helps us determine between man-made and natural features. Usually you can like really see a man-made feature just because it's very patterned. There's very regular patterns, there's sharp edges, etc. Natural features are kind of fuzzy. They have a little bit, they have sharp edges, but they're not patterned in the same way as man-made. So we tend to do a texture analysis to be able to determine stuff like that. So really what it is texture analysis is describing regions by quantifying its texture. So we often use qualitative words to describe texture. It's soft, it's bumpy, it's it's rough, it's fuzzy, those kinds of words, right? So you're going to see a lot of qualitative words for texture, but now we need to be able to quantify it because we're dealing with remote sensing and everything has to do with visual as well as numbers. So we can take a look at the intensity histogram. So we're going back to our histograms, and we're looking at how intense each pixel is instead this time around. So this way, this histogram will have the pixels on the bottom, and then it will have the intensity on the y-axis. So here we have our sum, which is the zi, which is a random variable indicating is the random variable indicating intensity. And then we have m, which is this here. So this is zi, which again is the random variable indicating intensity. And then p, which is my histogram of the intensity levels. So there's some pretty complex stats that go into this. You'd be like, well, now we got to deal with this pz. Okay, pz is a histogram. Now I'm looking at a function in that case and figuring out what the value is at z for that function. And then I've got the individual value of z from that actual pixel itself. And then L is the possible intensity levels. So every single intensity level going up that y-axis, I'm analyzing every single one. So this M, like it says, this is a mean intensity, so it's the average. And that's where it gets added up. P often can be referred to as the probability. You'll often see P used as, so this would be the probability of the histogram of intensity functions. Just depends on which exact texture analysis you're doing. So what is the probability of this occurring? Right? So that's why stats becomes really lots of fun. So besides the math, like I said, I'm not going to get you to do the math, but we're going to be using a probability function. We're using something called an intensity histogram, and we can calculate averages, and we can calculate sums. And that's going to give us numbers in the end. So here is a measure. There's different spectral measures of the texture. So there's the foyer, right? We just finished that. That when we are using these spectral measures, it describes directionality. So what way does the pattern point? So it's like, well, but okay, like why do I care? And so the reason we do that is because if it's very well defined up and down, then I can make like a wave of my data. I can say, okay, well, we know that it's trees and houses and then a road, and then trees and houses and then a road, and then trees and houses and then a road, and then there's a whole bunch of rocks. So if we're using that as an example, then I can go through and say, okay, what's my directionality? Well, my trees and rocks, or my trees and houses, sorry, have a lower reflection, and my road might have a higher reflection. So now I'm going to start drawing a curve showing that the texture actually follows a curve. And so that's what that means. When we have high spatial frequency, so that's like the tree house, everything on a property lot, it means that there's a lot of spectral changes in the area, and same with the low spatial frequency, right? So the area is more homogeneous. So if it's a low spatial frequency, the texture is going to be considered kind of smooth. If it is a high spatial frequency, then it's going to look very rough. So here's what I was talking about with the waves. So if we have a high frequency square wave, you can see that it's black and then white and then black. So we end up with this nice square. So this is, we could describe this numerically through a mathematical function. We can do low frequency, so look at they're bigger, right? So the waves are a little bit larger, and so that's a little bit, again, easier for us to describe as a mathematical function. Then we can get into sine waves. So you can see how really dark to really light is going to create higher and lower intensity values. And if it's a low contrast, it's lower high and low intensity values. So you can see how that impacts the contrast themselves, can impact the spatial or the frequency intensity. But you can also see how you can have a continuous versus a discrete texture analysis as well. So then we can take it and then we can filter out frequencies. So here we have our image and we have blacks and whites and grays, right? And then we can take out the high frequencies, so it kind of blurs it a little bit, even though this is still black, right? And then we're still going to see white, but the transition is a little different. And then here's the low frequencies, and so we can see that all the edges and changes we can actually make out better here. Then I'm going to get in, so that's the texture analysis. This is what we're going to see. So if you are pulling out, you're doing your math, and you're pulling out the values, and you're attempting to create these cyclic graphs, and then identifying them and like suppressing them or increasing them, you're going to end up with these different results. Maybe not so much as like this almost charcoal looking drawing, but that's what the texture analysis looks like. So I'm going to get into the last bonus objective in this particular video. And the reason I'm doing it now, and it's not in the course outline, and the reason it's not in the course outline is because I have not put it in. So I've noticed that now, and that's going to be changing for next year. But I do need you to know this as well, because it is kind of an essential component to remote sensing. So data fusion. Data fusion is bringing different resolutions together. So this can be spectral resolution, different spatial resolutions. It can be different radiometric resolutions, different, not so much temporal, because then we're getting into change detection. But data fusion really helps us enhance our images a lot better. This is not a This is not a processing technique per se. It's more of the in-between. So it's between like processing and post-processing. It kind of falls in that area. So you would do this very last because you've already done your mathematics. So you cannot do mathematics with this one. Like once you've completed this, it's done for math. You can't do any more analysis on it. You now move it into post-processing. So and the reason we do this is because we have different sources. We have different, like it might be the same satellite, but in order for us to get it from like, August to December, I'm going to have very different impacts from the sun. And so the sun will be shining down on it, and then it's got different angles, right? We talked about this in radiometric calibration. It still maintains an impact though. So if we do data fusion, we can bring these different sources together, and as long as they're radiometrically calibrated, but it also helps kind of adjust a little bit for that too. So again, this is only visual representation. It's not, you cannot do math with it later. It looks pretty good, but it's less accurate. So, I mean, if you do it at the beginning because you're like, hey, I really want to get it to be a higher spatial resolution or spectral resolution, and then you have to include that statement in anything that you're doing, because you just say this is less accurate. But this is not a transformation. Okay, so this is not something that you would do as a transformation for your project. So some of the assumptions that we do with data fusion, or that we decide on, usually we just say that it needs to be acquired around the same date and time. So you're going to try to get it as close as possible. What's kind of neat about Landsat 8 is that it's got the panchromatic band with the multispectrals. So we can take a multispectral image and fuse it with the panchromatic, and it's done at the exact same time and day, so we don't have to worry about any changes. It also assumes that the images must register together. And again, because they're taking it at the same time with the same sensor, they register together well. And the last thing is that the general geometry matches and they spatially match. So they have to have the same corners. So there's a lot of assumptions that need to be included in our data fusion processing if we are going to do it. If you don't have a panchromatic band and you're really trying to put them together, there's a lot of extra steps that go with it to improve that resolution. So there are, I guess, 4, maybe 6 different kinds of data fusion methods. I'm going to talk a little bit about them here, and just the main ones. So the first kind of data fusion method is the spectral domain procedures. So this looks at an entire scene and the individual bands. So it doesn't look individual in pixels, it looks at all of the spectral bands and the whole thing at once. So this, it can only use 3 bands at the same time. You can't apply your entire image at once. So this is why it's only good for display purposes. So you use the panchromatic band that is with the sensor to be able to do this. And all it is improving spatial resolution, not spectral resolution. So the first one is called an intensity hue saturation method. It's also known as the hue saturation value method. And it looks at, so the intensity or value, those are the same thing. It's the brightness of the pixel. Hue is the wavelength of the pixel, and saturation is the purity of the hue. So how red is it? So the hue, the wavelength, it's like how red is it? Or like it is a red band. Saturation is how red is it, and then so what is everything else is removed from that pixel, and then brightness is just how intense it is. So the method to doing this is we're going to create an RGB composite of whatever bands that we want to use, and then we're going to convert the RGB to IHS. This is his there, but IHS or HSV. So you're going to convert that. That's actually a tool in the toolbox. And then it converts it to this other color theory. So this is a different color theory. So it looks really weird on the screen because your screen is meant to represent RGB. The mathematics behind the HSV make the conversion. So if I take it from RGB and I convert it to HSV, then the colors change based on this here. So it's not red, green, blue anymore. What's going to end up showing is hue, which is the wavelength. So it's going to tell you show the wavelength of the value of that in red, and then S, which is the saturation. So it's going to give you the purity value rather than giving you the actual red, green, blue. So it looks very different on the screen. It does, and really it does. So once you've converted it, you're going to rename and replace the panchromatic image. So the intensity image, I'm going to pull that out. I'm going to take it out of its slot, which is the intensity, because that's just telling me the brightness. And then I'm going to replace that with panchromatic. So now instead of being an HSV image, it is now an HS panchromatic image, right? Hue, saturation, and panchromatic. Then I can convert it back to RGB, so kind of reverse it. And then I have a fused image that is an RGB image with a panchromatic band as its intensity that has been switched back, right, to RGB. So again, so you create an RGB composite, you convert it to HSV, you replace the intensity band with the panchromatic band, and then you convert back. Again, all it does is improve the spatial resolution. So you can think like with Landsat, we have a spatial resolution of 30 meters on the multispectral bands, and then it goes down to 15 meters. So I'm actually improving it by 200%. Right? So the other way we can do it is the principal component transform. So you've done a PCA because you're like, I am going to be a diligent remote sensing person, and I'm going to do the PCA. And then what you're going to do is you're going to take the PCI, or 1, PC1 band. That's the trend band, right? Because that's telling me like, oh, what is all the major things happening here? And I'm going to replace that one with the panchromatic band. And then I can inverse it, and I now have a new spatial resolution. I apologize for all these videos. Spatial is always written as special, and I'm not sure why that is. It's supposed to be spatial. So I don't know how I did that. I must have been like spell check or something when I was typing. Anyway, so so I take a PCA. I have 3 PCA bands. I have PC1, PC2, PC3. I remove PC1. I put in the panchromatic band, and then I inverse the PCA so that I can combine that panchromatic band with the other bands. And then now I've got a new composite with the panchromatic band. So then the third one is called a high pass filter technique. So I apply a high pass filter to the image with the high spatial resolution. And then that one extracts and isolates the high frequencies. And then I'm going to synthesize it with this multispectral image. This is where we get into something fun called wavelets. If you are going to be doing wavelets, you are working with probably microwaves, or you're working with like the frequencies of all of your images, and you have a lot of time to wait for computers to process. So you're probably doing research at that point. So if you're working in a research group, awesome, wavelets are a way to go. Otherwise, really, it's just you isolate those high frequencies, and then you're going to include it all together into the whole system. So really what it does is it just highlights those edges, right? Because that's what a high frequency does. So it's highlighting those edges instead of actually changing the pixel size itself. Then the second type of methodology for data fusion is algebraic. And so this one operates on individual pixels rather than the whole thing at once, where the other one is like, okay, I'm going to take out a band and put in a band. This time around, I'm going to have every individual pixel that I look at. There's 2 that I talk about here in this class. There's obviously many more. And so the first one is the Brovie transform. And it finds the proportional brightness in the band and replaces the proportion with the high spatial resolution image. So again, it's a linear equation. Operates. You can put it into mathematics if you really like. You can imagine that you take the brightness, you take the panchromatic, and you're kind of putting it together with the proportion of the brightness. So you convert it into brightness, and you find out each band how much of the total brightness each band is. And then as you go through, you take your high spatial resolution and you kind of fuse it together with it in terms of, okay, this group of pixels has the same proportion altogether, so I don't need to increase the spatial resolution for that. Now this area has a lot of high spatial frequency, so I'm going to adapt that high spatial resolution image to that particular area. So it does maintain my spectral integrity because I'm not actually removing any bands. I'm just taking my panchromatic image, and I'm trying to adapt my image based on what I'm finding in terms of brightness. So pan sharpening falls into this process, into the Brovie transform. You will find it separate in Envy. We'll be doing the Gram-Schmidt one. It's just because I've found that depending on the computer, different computers and different ways of us processing things, sometimes the Brovie doesn't work. So we're just going to go with yes, it's going to work, and we're going to do the Gram-Schmidt, but it falls into this particular data fusion method as well. Then we also have the multiplicative model, MLT. This one's really easy. You take your panchromatic image and you take every band and you multiply them together, and then you take the square root. So the panchromatic image that you're putting it with it takes on those lines of where the pixels end and begin. So I take it, I multiply them together. I end up with a large number because I'm going to have my intensity values for each of them that's squared. But because the panchromatic image, if there's different colors of or different intensity values of the panchromatic image, let's say 4 of them, in one single pixel of the coarse resolution, it's going to be split into 4, right? Because they're matched perfectly. And then each of those 4 values of the panchromatic image are going to be multiplied with that single value of the coarse resolution image. Then now I have 4 different values of that same area. So that's what the multiplicative model does. So it increases that spatial resolution merely just based on that. But make sure you take the square root at the end once you've added them or multiplied them together, just so that you can get it to even out. So this one, it's kind of the geometric. When you take the square root, it's kind of the geometric mean of the 2 of them. And it usually has a weight that we can apply to maintain the brightness value, because sometimes we end up with issues of one being much brighter than the other one. So that's that one's easy to code yourself. Like you can just go into the band math and do this one on your own to see, and it should work. Sometimes it doesn't. Again. And once we start getting into some of these more complex processes, even though it's a very simple mathematical thing, if it's not exactly what MV expects, sometimes it won't work. So, but the multiplicative model is really quite straightforward. So there's some more references for you if you want to go check them out. And that wraps up our last module, or not last module, but module 5. So next week we'll be getting into module 6.